speaking on the domination theory. It comes under the graph theory. It is there for the syllabus for MSc 4th semester at Gulbarga University. To know about the domination theory, the reference book is written by V.R. Kulli. You can refer it. Let's know about, to know the meaning of the domination, you should know about the open neighborhood, and closed neighborhood. With reference to a graph, we shall consider. Let there be a graph, label it. Labeling in the sense that these are called the vertices, whereas the lines are, we refer into the edges. Labeling or giving some names to the vertices V1, V2, V3, V4. In this case, to define the open neighborhood at the vertex V1, we do write it as n of V1 is equal to, it is the collections of those vertices. It is the collections of those vertices. This capital V stands for it is the set of the vertices where V1 W is referred to be as an edge, or in general you can also take up here V is any vertex belonging to the vertex set. That means you know that here what are the members of capital V? You have V1, V2, V3, V4. You can also name this as a graph G, right? Now, writing with this definition, you can write it as, now see that which are the vertices adjacent. It means to say that the vertices are said to be adjacent means they are joined by a line, right? Here, V1 is adjacent with V2. V1 is adjacent with V3. So therefore, the set containing V2, V3, this is the set we call it as the open neighborhood with respect to the vertex V1. Similarly, you can also see that what is the open neighborhood of V2? The open neighborhood of V2 is V1, V3. The open neighborhood of V3 is V1, V2, V4. The open neighborhood of V4 is only V3. Likewise, we can define the open neighborhood of a vertex. And the closed neighborhood can also be defined. And here we are using the square bracket. N of any vertex V is defined to be it is the union of the open neighborhood of V union, that is inclusive of the corresponding vertex. Inclusive of the corresponding vertex. Say for example, as already we have noted that the open neighborhood of V1. Now, what is the closed neighborhood of V1? Closed neighborhood of V1 is equal to the open neighborhood means it is V2, V3 union the vertex V1. So with that you have the closed neighborhood is called as it is the set containing V1, V2, V3 inclusive of that corresponding vertex. Now we can know about what is the closed neighborhood of the second vertex V2. It is V1, V2, V3 and V2. Closed neighborhood of V3 is V1, V2, V4 and V3. Closed neighborhood of V4 is V3 and V4. So likewise we can define the open neighborhood and the closed neighborhood of a vertex with reference to the given graph. Then let's know about the meaning of the domination. Domination of how to define domination. If any two edges in a graph, if any two vertices are said to be adjacent, then we said that the corresponding vertices are said to be dominated by each other. That is the meaning of the domination. Now with that we have let us know about the meaning of dominating set. With the meaning of domination. Now take an example. Suppose G is the graph. Label it. This is the graph. We have labeling the graph. Here we say that V1, V2, V1 here 1 and 2, the vertex 1 and 2 are said to be adjacent. So correspondingly they are said to be dominating each other, right? And with the meaning of this domination, here look at the vertex 4. The vertex 4 is adjacent to 3, 2 and 5. So mutually they are also said to be dominated each other. Followed? So with this you can write it a set containing those vertices so that all the vertices in the graph should be dominated by the other vertex. For example, I will consider here if you take the vertex 2 and then if you take the vertex number 5, if you take the vertex 2 and the vertex number 5, see here 2 is adjacent with 1. We say that on the other hand it is dominated to vertex number 1, 3, 4. The coverage you are seeing that the vertex 2 is with the domination covering 1, 3, 4 and whereas the other vertex 5 is said to be adjacent to 4, 6 and 7. So therefore 5 is also covering or dominating the remaining vertices 4, 6 and 7. Now we can call it as this is the one dominating set with reference to this. Similarly, we can also have, suppose if you take up as 1, right? 1, then 3, 6, 7. Here 1 is dominating 2 and 3 is dominating the next 4, right? And 6 is dominating 5, 7 is dominating 5, right? So if you have chosen only in this set to say about the controversy of the not dominating set, by the removal of any vertex from this, say for example, if I remove the vertex number 1, take up only those vertices 3, 6 and 7, is it any vertex is dominating 1? No. So therefore, this set cannot become the dominating set, right? So such a set is said to be minimal dominating. It should not lose the definition of the domination by the removal of any vertex. This is also called as a dominating set. The first one is also called a dominating set. Similarly, you can also see here another example 2, 6, 7. Look at 2. The vertex number 2 is dominating 1, 3, 4. And what about the remaining ones? So for that you have to choose 6 is dominating 5, 7 is dominating 5. Or else you, in place of 6 and 7, you can also introduce 5 and with that you are getting this. But whereas by the removal of the vertex 6, 6 is not dominating 7. So therefore inevitably you have to choose both 6 and 7. Now you have, these are the kinds of the dominating sets. We write it as in general as D set. And to know about the minimum, the cardinality, we use the symbol as this symbol as we have referring for the modulus sign. For example, the cardinality of the set 2, 5. This is what we call it as cardinality of a set. The meaning of the cardinality says that it is the number of vertices or the elements occurred. For this you have it is 2. 2 elements or the 2 vertices are here. Similarly, tell me what is the cardinality of the second set? It is 4, and the cardinality of the third is 3. Thus, with that you have the minimum dominating, all are said to be the minimal dominating sets, no doubt at all. We write it as MD set, minimal dominating set. It is losing a dominating set. First thing is you have to see that it is a dominating set or not. And to check that it is with the minimality of the domination, as you have to see that the meaning is by the removal of a vertex, it is losing the definition for the domination. So therefore, such a set is said to be the minimal dominating set. Because you can see on the other hand, the set containing 1, 2, 4, 5, 6, 7. This set is also a dominating set, no doubt at all. But the thing is, in this, if you remove 6, it is not losing its domination property because 5 is there. The vertex 5 is there for dominating 6 and 7. If you remove 6 from that set, it is not losing the domination property. So this cannot be called as a minimal dominating set. Minimal dominating set. Not necessarily all the dominating sets are called the minimal dominating sets. Now here among the dominating sets, and that you have to choose minimal dominating sets. Among all the dominating sets, you have to choose which is having minimum cardinality. The set which is having the minimal cardinality, and that is referred to be the domination number. That is called as the domination number and is denoted by small gamma of G. Now, the gamma of this graph G, gamma of the given graph G is equal to 2. Now, you have also seen that the cardinality of other minimal dominating sets also. With reference here you have 4. 4 is the maximum number, and that 4 is which is the maximum number of the minimal cardinality of the set, having the maximum number, and that will be called as the upper domination number. We use it as capital gamma of G. With this you have 4, where we call it as the domination number. Small gamma of G is we use it lower bound, and that maximality is used for the upper domination number. Upper domination number. So this is about the domination number. And you have the domination number if the given set is a dominating set and its complementary set in the vertex set is also be a dominating set. If in a given set, if any set, a minimal dominating set, if D is a minimal dominating set, then we also see that its complement set is also a dominating set. For example, we shall consider this is the set. We denote it as P3. Path with 3 vertices. Now in this, you have the set containing V2 will act as the minimal dominating set, and also you have the other set V1, V3 will also act as the minimal dominating set. In this case, you have the two minimal dominating sets. By the removal of any one vertex V1, the domination property is disturbed. The domination definition is destroyed. So that should not happen. So this kind of sets are called as the minimal dominating sets. And the cardinality, that is gamma of P3, in this case you have 1. But in this statement we have to prove for, if D is the dominating set is a minimal dominating set, its complement set is also a dominating set. That is what you are observing here, isn't it? What is V minus the set containing V2? This is what we are writing as the other two sets. Is also a dominating set that you are observing. Or V minus the set containing V1, V3. This is what we are referring as the set containing V2. In this reference, you are seeing that both will act as minimal dominating set and the complementary set is also a dominating set. Now, for some of the important graphs, we can calculate what is the domination number. For some of the graphs, domination number of PP, domination number of CP, then domination number of KP and domination number of any bipartite graph. Any bipartite graph. For the first one calculation, let us see P is equal to 2 onwards, we shall see it. And the one thing here you have to notify that for a trivial graph, or we say that a graph is an isolated graph, you know that its degree is 0. And we say that it is dominating itself. So that if the graph is having an isolated vertex, if the graph is having an isolated vertex, it is said to be dominating itself. So the domination number is 1 is added if the graph is containing an isolated vertex. We'll begin with for P2. P2, right? And the domination here is, domination number is, whereas you have got the two vertices, they are dominating each other. The domination number of P2 is equal to 1. Then the domination number of P3. P3 having the path with 3 vertices. In this case, the domination of P3 is 1. Next we can go for P4. The domination number of P4. In this you have the domination number of P4 is equal to, take any two alternate vertices, that gives the domination number you have. You have 2. And the domination number of P5. P5 is, P5. You are writing as with 5 vertices, right? If you choose any 2 vertices, the domination number of P5 is 2. And the domination of P6 and so on, you can get it. But here, looking at the generalization of the domination number, the domination number of Pn, or you can also, n is referred to be the number of points, or you can take up as here I have taken P, domination number of the path with P vertices, we can write it as it is n by 3. You have to take up as, this is what we call it as the smallest integer function. The smallest integer function. For example, here calculate for P2. n is defined to be the number of vertices given. Now here you have 2, 2 by 3, 2 by 3 you are come across it. 2 by 3 is now writing as specifically with the smallest integer, you are writing as 2 by 3. Now this is approximately, the value is coming out as 0.66 recurring. Now as you have to take up only the integer, this is the value 0.66 which is lying between 0 and 1. For the smallest integer, you have to take the greater value. Here the greater value is 1, so therefore we assign it as 1. So with that you have to choose it as the value is equal to 1. That is the meaning of the smallest integer function whose definition says you have to take up the greater value. Now for example, you take here gamma of P5. What is you are getting as here 5 by 3. 5 by 3 you have. 5 by 3 and whose value you can notify as 2.66. Not 2 point, it is, sorry, 1.66. 1.66, again with this reference in the range you have to choose it. The range is in which region it is lying down. It is in between 1 and 2. And here the upper value is 2. So therefore the value correspondingly you should take it 2. Is not the domination number of P5 is equal to 2 on referee. So this is the value, this is the general value, generalized value for the domination number of any path of length. Similarly, you can also calculate what is the domination number of any cycle. You know that the cycle is, we starts from C3 onwards. C3 is this graph. For C3, you have the domination number is 1. For C4, you have the domination number is 2. For C5, the domination number, you can take up any opposite vertices. So with that you have the domination number is for C5 is also equal to 2, and the next one, domination number of C6 is any two opposite vertices. There also you will see that it is 2. The domination number of C7, here you need to take the 3 vertices. Now what is the general formula for getting the domination number of any cycle? The domination number of any cycle Cp is also referred to be as the smallest integer of P by 3 or n by 3. If you are using n, you can also use here. It is also referred to be the same. Now check out for C5. C5 again you have, it is 5 by 3 comes out as the value 1.66 recurring, and its higher range is equal is 2. So therefore you have the domination number is 2. For the smaller cycles we can easily find out what is the domination number. Now here for C7, 7 by 3. 7 by 3 is 2.66 recurring, whose greater value is 3. 2.66 is the value lying between 2 and 3. In this range or in this region you have the greater value is 3. So with that we can write it the generalized formula as the domination number of any cycle is equal to the smallest integer function defined by P by 3 form. And the next one is complete graph. Complete graph is, it is a graph in which every pair of vertices are adjacent. And the first one we can take K4. Of course you can take C3. Already we have taken as C3. C3 or K3, it is 1. Now for K4, in which every pair of vertices are adjacent. So that the domination number of K4 is equal to 1. K5 is this graph. K5 is this graph you have, in which every pair of vertices are adjacent. Then the domination number of K5 is equal to 1. Now looking at the definition, we are seeing for complete graph, every vertex or every pair of vertices are adjacent with each other. So we need the only one will act as the vertex, the set containing only any one vertex will act as the minimal dominating set, and that minimality is referred to be the domination number. So with that we can write the meaning of the generalized form for in the calculation of the domination number of Kp is equal to P. Domination number of any complete graph is, it is equal to not P, sorry, it is 1 only. Domination number of Kp is equal to 1 only, because every pair of vertices are adjacent. Now for the bipartite graph, as the definition says, bipartite graph itself, the vertex set is divided into two subsets. If the vertex set V is given, we have the two subsets like V1 and V2, so that the definition for the edge set is defined to be as, the edges are referred to be the vertex from V1 made adjacent with the vertex from V2, whereas the vertices belonging to either the subset V1 or the vertices belonging to V2, they are not adjacent. So this is the meaning of bipartite. Bi means two. The two division of the, or the subdivision of the two vertex subsets, referring as M and N are the number of vertices. M is in V1, N is in V2. For example, if I take it as the first one is K23. K23 is the vertex, two vertices on the one side and the three vertices on the other side. Its domination number is the domination number of K23. It is equal to 2, because these two vertices are not adjacent. Of course, the other three are also not mutually adjacent, but we should take the minimum cardinality, therefore choose only two vertices. The domination number of K23 is 2. Similarly, for K33, the domination number of bipartite graph 333, we get it as 3. Then the domination number of K34 is it is 3. So with that, the generalized form for any bipartite graph, domination number of Kmn is equal to M only, because we have M is less than or equal to N always for any bipartite graph. So likewise, we can define the domination number of any path, domination number of any cycle, and the domination number of any complete graph, and also the domination number of any bipartite graph.